Good day, future engineers. We are going to continue our discussion on numerical integration, or also called the numerical quadrature day. So quadrature and integration, they just mean the same thing in our current definition on quadrature. So last time, we have already discussed the two methods to find the integral of the given curve with a function f of x. So moto siya we have the trapezoidal rule and the Euler's method. Right now we are going to tackle a new method in order to estimate or approximate the integral of a certain curve. Simpler functions use integration to find area under the curve of the graph, and while the more complex functions require only estimating the value by splitting the area under the graph separately with the use of many variables is known as numerical quadrature, or also known as numerical integration. So we have three methods here mentioned. We have the trapezoidal rule, the Simpson's rule, and the Gauss-Legendre quadrature. We are already done discussing trapezoidal rule, then right now we're going to tackle the Simpson's rule. So we have already defined, we have already discussed that if we have a curve here, to get the integral of that curve, we are going to get the area beneath that curve. Since this is just numerical integration or numerical quadrature, we need to have an upper limit. Let's say this is the the lower limit, the A, and the upper limit, the B. See, we are only dealing with definite integrals in this discussion. So we have discussed that to get the area beneath the curves, we can use the trapezoid. We get the area of the trapezoid beneath the curve, then we have already the approximate integral of the curve. Since si trapezoid, di ba? Since trapezoid is linear, to compensate for the error, not to minimize the error, we can have several intervals or areas beneath the curve so that the error will diminish. So just like this example, instead of just using the big trapezoid from end to end boundaries, in this example, the area beneath the curve is divided into three areas. So instead of this error, by using a single trapezoid, the error became lesser. And the more intervals or areas or slices that we, or more trapezoids that we will consider in the calculation, the lesser the error will be. However, since this is a line, it means that if we compare it to a higher degree, the curve, it has more errors than the curve. See, trapezoidal rule, this is from the linear interpolation, so we are using the line here. To approximate the area beneath the curve, so we can have a better integration, numerical integration, we introduce already now the curve. So from the first degree, we have the second degree or the third degree. By using this one, the estimates becomes better and closer to the original value. So si Simpson's rule, nani siya duha ka part. The first one is the Simpson's 1/3 rule. So the Simpson's 1/3 rule is based from the quadratic interpolation. Quadratic interpolation. Since this is a quadratic interpolation, it means that for a certain curve, we need 3 points, diba? Just like in the linear interpolation, we need 2 points to form a line. In the quadratic interpolation, we need 3 points, as shown in the figure, to form a curve. The curve that forms is a parabola. And this is of a second degree na curvature. So by applying the concept of this one, by applying the quadratic interpolation, our estimates for the integral of the curve becomes much better. So unsaon man ni siya pagkuan? Unsaon pagkuha sa quadratic interpolation for this one, for the Simpson's 1/3 rule. So we're going to discuss that in the next presentation.